Okay, our second example problem dealing with standing waves is going to be dealing with standing waves inside of columns of air, not inside of a string that's fixed on both ends. So problem 2 says, 3 identical tubes contain the same amount of water, which is 0.7 meters below the top of each tube, as shown above. When a 122 hertz tuning fork is held over the left tube, it produces a standing wave pattern as shown in the column of air above the water. And just to note, the standing wave pattern illustrates the particle displacement nodes and antinodes. Remember, when we try to graphically show what's happening to it inside of a column of air with standing waves, we can either show displacement nodes and antinodes, where the air is, let's say here, where there's a displacement node, it's not moving back and forth from its equilibrium position, and its equilibrium position is, let's say, right here. Displacement antinodes at the open end would be where the air is shaking back and forth the farthest from its equilibrium position. Or instead, we could graph what's happening to the pressure at each position. Here, where the fixed end is, the air can't move from equilibrium, so there's a displacement node. But the air gets compressed the most and stretched out the most at that location, so that's a pressure antinode, where the pressure is varying the most from the equilibrium pressure if there was no sound wave moving through there. And at the open end, the air gets displaced the most, but its density changes the least, and so the pressure is maintained at about equilibrium right there. But I find it easy to represent the displacement nodes where it's not shaking back and forth from equilibrium, and the displacement antinodes where it is just being disturbed the most from equilibrium. So it says, for part A, use the given information to calculate the speed of the sound waves moving through the air in the tube on the left. This will also be the speed of the sound waves moving through the air in any of the tubes. And so we've got our 122 hertz tuning fork. It's moving through there at some speed. And in this 0.7 meter length, how much of a wavelength fits in this 0.7 meter length? Well, from a node to an antinode is just a quarter of a wavelength. And so that 0.7 meters is just a quarter of the wavelength of the sound wave that's coming off of that tuning fork, which creates that particular standing wave. If we think back to our last example problem, we rearranged our equation for wavelength and frequency to solve for the velocity. If we just rearrange that equation, we get velocity is equal to frequency times wavelength. So we know there's a 122 hertz tuning fork that's vibrating back and forth at 122 times each and every second. That's producing our wavelength. And we know that a quarter of the wavelength fits in 0.7 meters. So therefore, one wavelength is going to be 4 times 0.7 meters. It's going to be 4 times longer than that 0.7 meter column of air. So 4 times 0.7 is 2.8 meters. So the wavelength is 2.8 meters. So if you have a sound wave that has a frequency of 122 hertz and a wavelength of 2.8 meters, let's figure out what the velocity of that sound wave actually is. So 122 hertz times 2.8 meters gives us 341.6 meters per second, which is pretty close to the accepted speed of sound in room temperature air. So at 20 degrees Celsius, the speed of sound is about 343 meters per second. Part B asks us to, in the middle tube, draw the next possible standing wave pattern, which would be produced by a higher frequency tuning fork. It says calculate the needed frequency the second tuning fork would need to produce this type of standing wave. So our 122 hertz tuning fork that produced a wavelength of 2.8 meters, only a quarter of that wavelength fit inside of that column of air. And if we have the same length column of air, right, in each of these other examples, there must be other possible standing waves which can be created in that same length column of air. Just like in our previous example, right, there were different types of standing waves which could be created in the same length string fixed on both ends. Well, we don't have a string fixed on both ends. We just have a column of air, and it doesn't have two quote-unquote fixed ends. It has one fixed end and one that's open, right? And we have to remember, what are the different possible standing waves with a closed and an open end? Well, the only criteria is that the closed end has to have a node, so in either of these locations, and the open end has to have an antinode. Well, if we can't put a node there, we've got to put a node somewhere else, so an antinode is there. So the first possible one has one node here and one antinode there, so it's a quarter of the wavelength that gets created. That sets up the standing wave. And the next possible one is going to have not a quarter of a wavelength that fits in that length, but 3/4 of a wavelength that fits in that length. And so we have to draw a standing wave so that in those same 0.7 meters, we have a quarter of a wavelength that fits in there. Well, this is a little tricky. So we draw a node here, and if we want an antinode here, which is 3/4 of the length, we need to draw another node that's half the wavelength. So half the wavelength would be about here, so that at the open end, there's the antinode. So we have like the first half the wavelength and another quarter of the length. And so drawing that standing wave would look something like this. We're going to start at the node. We're going to start to draw a sine wave. Go to the left, start to go to the right, but at the open end, we don't end at a node. We end at an antinode where it's the farthest from equilibrium. And I'm going to kind of draw what the other side looks like. Remember, these lines do not represent, like strings, what the air is doing. This represents here that here the air is not shaking back and forth. You know, the sound's moving up and down in the y direction. So air particles, when they get disturbed, are being disturbed in the y direction because this is a longitudinal wave. The particles get disturbed parallel to the direction of the wave travel that's bouncing off there and going through there. But this is just a graphical representation of where in the tube the air is displaced the most from equilibrium and where it's not displaced. So here the particles are shaking back and forth the most, and here they're shaking back and forth the most. Here they're not shaking back up and down, and here they're not shaking up and down. Well, let's go down and figure out what that frequency is. So calculate that needed frequency. So I'm just going to use this version of our wavelength and frequency equation and solve this for frequency by dividing each side by wavelength, and we get frequency is equal to velocity divided by wavelength, just to make this a little bit faster, simpler. So we figured out that in the left tube, the waves are moving at this speed, and as long as the air hasn't changed temperature, it doesn't matter what frequency sound waves we're producing or what frequency tuning fork we're using, all waves will be moving off at this speed right here, 341.6 meters per second. So even in the second tube, the wave speed is the same, 341.6 meters per second. And we just need to plug in how big is the wavelength created by this tuning fork. Well, we know 3/4 of the wavelength fits within 0.7 meters, so let's make a little equation. 3/4 of this, call this wavelength number 2, fit in 0.7 meters. And like here, let's call that wavelength number 1, because they're different frequency tuning forks that will create different or produce different wavelength sound waves. So I'm just going to turn this into decimal equivalent. So 3/4 is 0.75 times wavelength number 2 equals 0.7 meters. So wavelength number 2 is going to be equal to 0.7 meters divided by 0.75. This is essentially an algebraic equation we can solve for the wavelength. So how long does the wavelength need to be created by that second tuning fork? You just take 0.7 meters divided by 0.75, and we get that the wavelength needs to be 0.93 meters long. Well, let's go back here now. What frequency would you have to, would the tuning fork have to shake back and forth at to produce that particular size standing wave or length standing wave? Well, it's take the speed divided by the desired wavelength. So the speed, 341.6 meters per second, divided by the desired wavelength of 0.93 meters. So 341.6 divided by 0.93 gives us a frequency of 367 hertz. Okay. So it would need to be 367 hertz. And that wavelength, we'll call that wavelength number 2, we said needed to be 0.93 meters. Just to kind of compare to the first. And similarly, the last part of the problem has us thinking about the next possible standing wave pattern, which would be produced by an even higher frequency tuning fork. And we're going to calculate the needed frequency for this third tuning fork would need to produce this type of standing wave. So we're going to go back up to our diagram, and we need to first draw what that standing wave looks like, or a graphical representation of the displacement nodes and the displacement antinodes. And for standing wave problems, the first thing you should always do is draw a graphical or diagrammatic representation of the standing wave to help you figure out how much of the wave, partial or whole, fits inside of that column of air. So here's our second possible standing wave. The next possible standing wave, remember, it still has to have a node at the bottom and an antinode at the top, but it has to fit more of the wave than 3/4. So the next possible one would be 5/4 of a wavelength that fit inside of this length air column. So we're going to draw one. So let's say this would be 1 1/4. So from here to here would be 1 full wavelength plus 1/4. So now I'm going to draw our third node. So we go draw our little sine wave. We've got here's our first wavelength and 1/4. 1 plus 1/4 is 5/4. And I'm going to kind of draw the other part of it with our dashed line like we've done before. So that right there shows 5 1/4 wavelengths, or 1 and another quarter that fit in that length. And so now let's just solve for that up here. We can see that 5/4 of, we'll say, wavelength number 3 fits in that same length, that 0.7 meters. 5/4 is the same thing as 1.25. So I'm going to simplify it a little bit just to make a decimal equivalent. So that means wavelength number 3, or the size of the wavelength created by this third tuning fork, is going to be 0.7 meters divided by 1.25. So wavelength number 3, take 0.7 divided by 1.25, we get that the wavelength that the third tuning fork would need to create, the sound wave's wavelength, is 0.56 meters. So let's now go down here and use our same rearranged equation to solve for frequency using the values that we know. So again, the sound waves are all still moving at the same speed through the same temperature air. And we figured out, using our diagram up here, that the wavelength that needs to be created by this unknown frequency tuning fork needs to create whatever it is, has to be, the wavelength has to be smaller than 0.7 meters, and 5/4 of the wavelength has to fit in there. And that would yield a wavelength of 0.56 meters. So we're going to divide this by 0.56 meters. And maybe it'll be helpful to say that, like, the third frequency is equal to the wave speed divided by whatever the third wavelength is. So that's wavelength for the third sound wave. It's 341.6 divided by 0.56 meters. We get that the frequency of the third tuning fork would need to be about 610 hertz, which is another higher possible frequency, which would create a standing wave inside of that same length column of air.